Quality Control and Improvement, Module 6, Lecture 3, Control Chart Decisions. So the main objective for Lecture 3 are to understand the advantages and disadvantages of attributes versus variables control charts. Almost any process will benefit from applying statistical process control, including the use of control charts. In the next slides, we will present some general guidelines helpful in implementing control charts. We'll determine which processes are characteristics of control. We'll list some advantages and disadvantages of the different types of control charts. And we'll take actions to improve processes as a result of control chart analysis. Among the most powerful techniques for producing good quality are those of statistical process control and process improvement. A well-designed process will produce good products of the desired amount, on time, and at the lowest cost. Good process control can also contribute to identifying any areas of product design and process that need improvement. Control charts should be applied to any product, characteristic, or manufacturing operation believed to be important to management. At the beginning of a control chart program, there will usually be more attribute than variable control charts. However, as we learn more about the process, the attribute charts will typically be replaced with variable control charts to refine the process or product. In many applications, the analyst will have to choose between using a variables control chart, such as the X and R charts, and an attributes control chart, such as the P chart. In some cases, the choice will be clear-cut. For example, if the quality characteristic is the color of an item, such as might be the case in carpet or cloth production, then an attributes control chart would often be preferred over an attempt to quantify the quality characteristic color. In other cases, the choice will not be obvious, and the analyst must make or take several factors into account in choosing between attributes and variables control charts. Often the case comes down to cost and how ease of implementation. There are several advantages of attributes control charts. Several quality characteristics can be considered jointly, and the unit classified as non-conforming if it fails to meet the specification on any one of characteristic. On the other hand, if several quality characteristics are treated as variables, then each one must be measured, and either a separate X and R chart must be maintained on each, or some multivariable control techniques that considers all the characteristics must be simultaneously employed. So in other words, variable control charts are much more complicated than attributes control charts. Furthermore, expense and time-consuming measurements may sometimes be avoided by attributes inspection. Variable control charts do have some obvious advantages over attributes control charts, however. They provide much more useful information about the process performance. The most important advantage of the X bar R and R control charts is they often provide an indication of impending trouble and allow operating personnel to take corrective action before any defective products are actually produced. This isn't the case with attributes control charts. Thus, X bar and R charts are leading indicators of trouble, whereas P charts or C and U charts will not react unless the process has already changed, so that more non-conforming units are being produced. Since we cannot perform quality control techniques on every aspect of a process all the time, another important decision is what to monitor. Some areas are less critical than others. Some points that are typically considered most important are the following. Inbound materials. These are typically materials coming into the process that are used as raw materials. This would be a good chance to check those out and make sure that these products are up to standards. Because if you start manufacturing a product with inferior materials, you're going to have problems down the road. Another point to consider is mission critical components. Are there some components of the process that are so critical that failure would result in lawsuits, safety concerns, warranty concerns, be very expensive to have to replace, etc. Another point to consider is at any point in the process that's very costly. If you're producing a product, some components are more expensive than others to manufacture, to install. So those kind of mission critical costly processing materials equipment you want to actually inspect at that point. And obviously, at the finished product at the end, you want to inspect and see if the product meets standards. The primary objective of statistical process control is process improvement. The application of control charts give information on two key aspects of the process. The first one is control, and the second one is capability. So taking these two things into account, we can sort of form this little table where we have four blocks. What we're graphing here is one is the process capable versus is the process in control. So if you look at the box in the upper left corner, this process is in statistical control and exhibits adequate capability for present business objectives. If this is the case, well, then SPC methods are very valuable here for monitoring and warning against occurrence of any new assignable causes that could cause slippage in performance. So these are processes that are up functioning. We've already established our control charts. Here we're just monitoring to make sure that problems don't develop. The upper right corner is a case where the process does exhibit statistical control but has poor capability. In this case, SPC methods may be useful for diagnosis of problems and improvement. Primarily here, what you're going to be looking for is patterns on the control chart. So here, the process is capable. However, it needs much more refinement to get either centered, through the analysis of your capability analysis, capability indexes, CP and CPK. We're trying to improve those here. Typically, what's going to have to happen here is you're going to have to intervene in this process, and you're going to have to improve certain steps of it. You may have to get new equipment, you may have to get new techniques, new tools for measurement, etc. The lower right-hand corner presents the worst case kind of scenario where the process is out of control and not capable. Here you're going to have to, this is where you need to start. This is probably, you're starting to develop your control charts. And so when you get these things up functioning here, in this kind of scenario here, you're likely to see rapid improvement because the process is just totally out of control and it's not capable at all. Here, the primary objective is try to figure out what the assignable causes are. Try to eliminate those assignable causes and get the process in control. So control charts are very valuable in that. So the lower left-hand corner treats a case where the process is capable but is not in statistical control. This may seem kind of odd at first, but really what this kind of means is that your specifications are too wide. You have it's not in control, but the specifications are so wide that it just falls within the capability. Here, SPC methods should still be used to establish control and reduce the variability, since the process here obviously experiences assignable causes, which may in the future lead to poor capability analysis. Well, this is the last lecture in this module, and I hope you enjoyed this module, and I hope you're enjoying the course. I know there's a lot to learn, but these techniques are very valuable in the real world.